Okay, now that we've talked about stability in atoms and we've talked about ionic compounds and how ionic compounds exist, let's look at naming ionic compounds. And this can be naming and it's formula writing. And so, naming ionic compounds, these are the kind of steps that we take when we're trying to name ionic compounds. In step one, we first write out the cation, and then we write the anion second. Now, cations consist, and I would make a note here, cations are normally going to be our metals. Okay, anions are normally going to be our nonmetals, or they can be polyatomic ions. Okay, but basically what we get is in an ionic compound, it is a metal plus a non-metal, and that's how we tell the difference between those. Okay, in metallic bonding, it's between a metal plus a metal. But in ionic, what we see is that we're going to have it between a metal and then a non-metal. So a cation will be the metal and the anion will be the non-metal. Now, the charges must balance to zero. So basically, we can't have a charge to it. So if the metal is going to have a +1 charge, the non-metal's got to have a -1 charge. They have to balance each other out. Or if we look at the metal has a +2 charge, then the non-metal has to have a 2 -1 charges, which balance that out. And we'll look at that in detail in just a second. And then number 4, this is a reference to covalent bonding, which we'll talk about later, but prefix units are not used. So we're not going to use any prefixes here. And that'll make a lot more sense when we talk about covalent, but always keep this in mind. We never use prefixes in ionic bonding. That's only for covalent bonding. Now, number 5, if the cation is a transition metal, the charge is specified with a Roman numeral. The interesting thing about our transition metals is that our transition metals can have different oxidation numbers. Okay, when we wrote the hill of oxidation numbers, we did group 1, group 2, group 13, group 14, 15, and 16, and 17, because those are the ones that don't change. Oxidation numbers of transition metals change, so we'll look at that too. And number 6, if the anion is an element, the end is replaced with an IDE ending. If it's not an element, we just write the polyatomic ion and then put its name. So let's look at an example. Now, when we're looking at this, this is going to be a bond between lithium and oxygen. So the first thing we do, we already have lithium and we have oxygen written. Okay. The next thing we do, we write down their chemical symbol, which this is lithium and that's oxygen. Now, where we got these plus and minuses, that comes back to what makes them stable. So when we looked at our hill of oxidation number, we looked and we see that our lithium is in group 1, so that's why it has a +1 charge, and oxygen is in group 16, and that's where we get the -2 charge, and this is what we just get from the periodic table. So once we have those, what we do is we take them and let's get that out of the way. And what we do is we crisscross them. We cross the charges for the subscripts. Okay. Now remember what I told you. The positives have to balance out the negatives. When we crisscross like this, we bring this 2 down and that 1 down. So that 2 went right here and that 1 went right there. It's just understood. We don't have to write the 1. We just leave it understood. But what we see is that, remember what I said, the charges have to balance out. So how many lithiums do I have? Well, I have 2. What's the charge of lithium? +1. So we have +1 and +1. And then oxygen, how many do we have? 1 of them. What's the charge of it? 2 negative. Well, the positives balance out the negatives, and we got a charge of 0. By crisscrossing, we get a charge of 0. Now all we have to do is name it. This is lithium. It's not a transition metal, so we don't need to put a Roman numeral for its oxidative state. And then we have oxygen, which we replace the ending of oxygen with IDE, and that's where we get oxide. So let's look at some polyatomic ions and what they are. Polyatomic ions, they're atoms that are treated as a single molecule. They can be both cations and anions, so they can be positive and they can be negative, and we need to memorize these. We have to have some of them memorized, the common ones, and we'll have a list of those that we'll memorize. But basically what happens, we got to have them. So when we talk about nitrate, nitrite, when we talk about phosphate, phosphite, we know what the formula is before we move on. Okay, let's look at some examples. This is a tough one. So it says the professor for your chemistry lab forgot to record the oxidative state of copper used to create copper sulfate. An in-depth mass analysis provided the empirical formula. Based on the available data, what is the oxidative state of copper? So how we named this? Well, it's very simple. We looked at Cu. Guess what? That's copper. We looked at SO4, and we know our polyatomic ions because we have them memorized, and we know that SO4 is going to be sulfate. Okay, so we have copper and then we have sulfate. So that's where we get it right here. Now remember what we said in our rules. If it is a transition metal, it has to have a Roman numeral to specify the oxidative state. So yes, this is copper sulfate, but we need to figure out what is the oxidation number of copper. To do this, very simple task. Okay, what you're going to do, we know the oxidative state of sulfate, because we memorized our polyatomics. We have SO4 with a -2 charge. Okay, so what we do is we set up the whole compound is going to be equal to 0. Okay, so 0 equals all the charges have to balance out. How many sulfates do we have? 3. 3 times its oxidative state, which is -2. 3 times -2 is -6. Okay, plus the other part of it, copper. Now, how many coppers do we have? We have 2. Do we know its oxidative state? No, so we just go X. So it's 2X. And then all we have to do is solve for X. So we bring the 6 to the other side, and we have 6 equals 2X. And then we divide by 2, and X equals +3. Now how we write the name? We write copper 3, 1, 2, 3, and then sulfate. And we only have to do this when you have a transition metal. Okay? Next example. It says write the correct molecular formula for barium oxide. So when we're looking at this, we look at our hill of oxidation number. Okay, look at your periodic table, and we'll look at it. Let's scroll back up, find a periodic table, and almost there. There we go. So here's barium. It's right there. What group is it in? It's in group 2. Okay, so when we look at our hill of oxidation number, we see that it is in group 2, so barium, which is Ba, will have a +2 charge. And oxygen, pretty common, we see that that's going to be in group 16, so oxygen will have a -2 charge. So all we have to do here is crisscross them to write the formula, and we get Ba2O2. When this happens, when their oxidation numbers are the same, you see how this is a 2 and that's a 2, you can reduce it to a 1 and a 1. So instead of having Ba2O2, you can reduce these down to a 1 and a 1. So barium oxide is just BaO. Now, ammonia hypochlorite. Okay, so ammonia, or ammonium is going to be NH4. It's a polyatomic ion. It has a +1 charge. Now, hypochlorite is going to be ClO with a -1 charge. So all we have to do is crisscross these guys, bring the ones down, and what we get is we'll get our NH4, 1, ClO 1. And we get ammonium hypochlorite. Now, since they're just ones, we don't need to write them. We can just take this away and just leave our formula as NH4Cl. Let's look at our last couple examples. It says write the proper name for, and then we see we have Ki, and then we have SnClO4. So on our first one, it's two elements together. Okay, the first one's potassium. So the first thing we do is we write potassium. Okay, we check, is potassium a transition metal? No, so it doesn't need a Roman numeral. So we look at the other one that we have, it's I, which we know that I is iodine. Now, anytime we have an ending and it's an element and the anion is an element, what we do is we go ahead and change the ending from iodine to iodide. We put an IDE ending. So on our first one, we get the name of potassium iodine or iodide. And we see on the next one, we have SnClO4. Now, again, we're going to go ahead and name these guys. The first one, Sn, we look on the periodic table, it's 10. Okay, now the ClO4 is a polyatomic ion. That's perchlorate. We also, you can see it called hyperchlorate, but we're just gonna write perchlorate. And since it's a polyatomic ion, we don't have to change the ending. Now, tin is not a transition metal, but tin does need a Roman numeral because tin can have multiple oxidative states. So it can be tin-2 or it can be tin-4. So to figure out what it is, we know that the whole compound is going to be 0. So 0 equals, and then we look at this. Chlorate or perchlorate is going to have a -1 charge. Well, how many do we have? We have 4 -1s, so that'll give us a -4. Plus the oxidation number of 10, which we don't know, so we only have one of them, so it's just 1x or x. So to solve for x, all we have to do is add 4 to both sides, and we get +4 equals x. And so what we do is we give the Roman numeral 4 to 10. Okay, so we get parentheses 4. So this becomes 10,4 perchlorate.